Okay, so one way to find the derivative, dy dx, is to use the chain rule. A second way to find that derivative, dy dx, is to go back here and eliminate the parameter to get y in terms of x directly, so you can find the derivative, dy dx. So let's do that. X equals t, y equals t squared. That tells me t is equal to x. Generally, what you do to eliminate the parameter, solve for the parameter for one of the variables, t equals x, and then replace that in the second equation. So y is equal to t squared, which is x squared. Now you have y in terms of x. We've eliminated the parameter. You can find the derivative, dy dx, directly. Okay? To get 2x. Now, you got 2x here, you got 2t here. They're both correct. Why? Because x is equal to t. All depends the form that you want it in. How are we doing? Everybody okay on this? Yes, Dan.
For the method where you're using the chain rule, can you leave it in terms of t?
You can leave it in terms of t. It depends on the problem. Generally speaking, however, if you're looking for dy dx, you want it in terms of x or y and not t. But sometimes it seems to be you'll be asked to find the derivative for a given value of the parameter, and at that point I would leave it in terms of t, certainly. But better form would be find dy dx in terms of x. That would be the better form. That's a good call. What about if it's difficult to eliminate the parameter? Let's do another problem. Let's suppose we have something like this. And this is something you're going to run across in WebAssign, I would assume. Let's suppose we know that x is equal to 2 sine t, and y is equal to 3 cosine t. Okay? And what we want to do is to find the derivative dy dx again. Let's find dy dx. And we want to graph it as well. We want to plot this graph. And we want to find orientation as well. We want to do all these things. Geez, so much time do I have to do this? All right. Okay. Let's do it. First of all, let's find dy dx. That's not too difficult. We can find dx dt. Okay. Take the derivative. Find dy dt. And then find dy dx by using the chain rule. And I'll make this -3/2 tangent t then. Okay? That will give me the derivative in terms of t. -3/2 tangent t. Can somebody see how to eliminate that t and get it in terms of x's and or y's?
Maybe square both x and y. Replace then using sine squared plus cosine squared 1.
Tan squared plus what?
Not sine squared plus cosine squared is 1.
Yes.
Make it use that relation.
Yeah, that's what. We can go right back to the beginning and do that and eliminate the parameter. Let's do it. We've got our derivative dy dx in terms of t, -3/2 tangent t. Let's leave that there. What he's saying to do, if we go back to the original, we can eliminate the parameter and get y in terms of x and do it that way. Very good. Let's do it. What you do here, and there's a little trick for this, is divide both sides by 2, isolate sine, divide by 3, isolate cosine, okay. Square both sides, and then do exactly what he just said. If you add up both sides, what happens here? If you add up this side, the left side, you get x squared over 4 plus y squared over 9 equals sine squared plus cosine squared. But what's sine squared plus cosine squared equal to? It's equal to 1. You've eliminated the parameter by using that Pythagorean identity with the trig functions, okay? Sine squared plus cosine squared is equal to 1. Now, we have x's and y's with no parameter. We've eliminated the parameter that way. We can find the derivative by using implicit differentiation, for example. Here, let's do it. Let's use implicit differentiation. Take the derivative, 2x over 4. Okay, you get 2y over 9 dy dx equals 0. Okay, I'm just taking the derivative with respect to x, implicit differentiation. I'm going to throw the x on the other side. I'm going to multiply both sides by 9 halves and divide by y. Okay, so I'm going to multiply by 9 halves. And I've got an x. And I'm going to divide by y. So now I have the derivative in terms of x's and y's. And watch this. Are these two the same? Well, check it out. X is equal to 2 sine. If you put a 2 sine in here, you'll get the 2's canceling one of the 2's here. The y is equal to 3 cosine. 3's will cancel. You get a cosine. You'll end up with a negative 3 halves sine over cosine, which is exactly what we had before. So we could eliminate the parameter by taking advantage of the Pythagorean identity and finding the derivative directly. That's a good call. And what do we have? What is this graph? It's an ellipse. What's the length of the semi-major axis? 3. Semi-minor axis? Okay, something like this. Okay, with a center at 0, 0. Okay? Orientation. To get the orientation, go back to the original. Okay? Let t equal 0. If t is equal to 0, x is 0, y is 3. This is our starting point. Increase the parameter t. If you increase t, what happens is the sine t will increase, x will increase, the cosine will decrease as you increase t. So x increases, moves to the right, y will decrease. That means we have this orientation. I'm going to tell you on your test, it's very likely you have a problem similar to this, where I'm going to ask for orientation, I'm going to ask for the derivative, those kinds of things, okay? Something like this, okay? Probably be on the test. High probability. High probability. Close to 1. What's that? The orientation you get by starting the parameter t somewhere at 0. Noticing that x will be 0 and y will be 3. This is the point that we start with. Then as you increase the parameter t, what will happen is the sine will increase. You can take a specific value, take pi over 4 or something like that. But generally speaking, if t increases, sine increases. Think of the sine curve. It increases. Cosine decreases as you increase t. So x will increase, move to the right. Y will decrease, move down. As you move to the right and down, it goes around the ellipse this way. Okay, with that clockwise orientation.
Yeah, but why would you start off from 0 and 3?
Because when t is 0, x is 0, and y is 3. It doesn't matter where you start. You want to start somewhere where it's easy. Okay, start somewhere easy. T equals 0 is the easiest place to start. I mean, you could start at bless you. You can start at negative pi over 3 if you want, but that's not the easiest place to start. Start at 0. Okay. Yeah.
Could you please move the paper?
Oh, where am I?
So it looks like, so you started the problem up there with the negative 3 sine t over 2 cosine t, right?
Yes.
And you started doing it that way, and then you did you sort of stop halfway through and then start doing it through the implicit differentiation?
Well, no, well, I don't think that's, well.
So
Here's what I did. I stopped here, we got the derivative in terms of t. And then we said, well, let's find the derivative. We want it in terms of x's and y's and not t's. So what he suggested is, well, let's eliminate the parameter. Let's go back here and eliminate the parameter, which we did, and then we could find the derivative dy dx in terms of x's and y's and not t by eliminating the parameter, okay? My thought at the time, I don't know how obvious it was to go here and replace the sine t with x over 2 and the cosine t with y over 3 and get that derivative in terms of x's and y's that way. But when he suggested that, we're going to have to do this anyways. There will be times when you want to eliminate the parameter from the beginning. So I figured, we'll do it that way. So maybe you noticed that there was a kind of a change there. That's pretty perceptive.
So could you also take the negative 3/2 t, or tangent t, and do like a trig substitution and rewrite it in terms of the Pythagorean theorem and then go back to x?
You could. Pythagorean theorem there, you know, you got tangent squared plus 1 is secant squared, so tangent's going to be the square root of secant squared minus 1. You know, that doesn't look promising. The sine over cosine thing is the way to go on that.
How would you get it to go the opposite way?
How would you get it to go the opposite way? Well, the easiest way is put a negative in front of the 2. That would get it to go the opposite way. If you had negative 2 sine t, you get the same ellipse, and it'll flip it, the orientation
Can
around.
you move it down a little bit?
Oh, yeah. If I put the negative 2 right here.
What about y?
You could do it there too.
No, so it's, but you can't put both of them.
If you put both, you'll end up with the same thing again. There's one more thing I want to do here, and that's the second derivative, okay? In parametric form. Now, once you've eliminated the parameter, that's not a big deal. You can find the second derivative here easily enough by taking the derivative of this derivative yet again. Just be careful. When you take the derivative of a y with respect to x, you've got to have a dy dx. But there's a way of doing it by not eliminating the parameter, by using a chain rule for a second derivative. And it goes like this. The second derivative, concavity, right, is equal to, now, when we took the first derivative, watch this. We took the derivative of y with respect to t over the derivative of x with respect to t. That's what we did to get the first derivative. What is the second derivative? The second derivative is the derivative of the first derivative. Okay? So instead of taking the derivative of y now, what I want to do is take the derivative of the first derivative with respect to t and also a dx dt. The only difference, a little tricky, but it makes sense. What we're doing now is taking the derivative of the first derivative instead of the derivative of y, okay? This dy dx is playing the role of y. So, in this problem, let's do it. Let's find the second derivative, okay? What we have to do is take the derivative of our first derivative. Now, our first derivative is negative 3/2 tangent. So I'm going to take the derivative of negative 3/2 tangent with respect to t over the same dx dt we had from before, and that's 2 cosine. That doesn't change. Okay? What's the derivative of tangent?
And it's secant x.
What is it?
And t is secant t.
No. Secant squared. Okay, derivative tangent secant squared. So we got a negative 3/2 secant squared over 2 cosine. Holy mackerel. Well, we can do something with this. This 2 I'm going to bring down to this 2. I'm going to get a negative 3/4. Secant squared is 1 over cosine squared. So I'm going to take this times 1 over cosine cubed. Not nice, I agree, but that's what it is. Okay? That's our second derivative. Okay? Negative 3/4 over cosine cubed. Now, can I get that in terms of x's and y's. How can I get that in terms of x's and y's, which may be more useful? How can I do such a thing? I could go back to here and take the second derivative. I got to tell you, this is not a fun thing to take this second derivative because you got a quotient rule in here. That's not bad. But you also have a dy dx in here that you're going to have to replace with this original one. It gets a little messy. Is there an easier way to take this one and get it in terms of x's and y's only? Yeah, exactly. We know what cosine's equal to. It's equal to y over 3. So we could say this. Okay? Because that's what cosine's equal to. Okay? Y over 3. Often this is the kind of thing you do with these problems. So what do we end up with? Who knows? We got a 27 down here. I think I end up with a negative 81 over 4y cubed, I think. Is that about right?
Yeah.
Thank you. Now, does that conform to what we have over here in our diagram? Ugh, I'm going out on a limb now. Okay, I'm putting it all out there. Okay, here we go. Let's take this first quadrant. The y's in this first quadrant are positive. Okay, y cubed will be positive. The denominator will be positive. The numerator is negative. This will be negative. That means in the first quadrant, second derivative is negative, which means the curve is concave down, which it is. That's good. Let's take second quadrant. Y's are positive again. Cube, positive, positive, negative, concave down again. Yes, these are concave down. Let's take the y's down here, second and fourth quadrants. Those y's are negative. I'm going to cube those guys. That makes it negative. Negative divided by negative is positive. That means these are concave up. What I'm saying is this agrees with the graph that we have. Okay? So we can be reasonably certain it's correct. How are we doing? Guys look stunned. Okay. Okay, you're welcome. All right, so here's what I want you to do for Monday. Monday, you should be on WebAssign. You should be done with homework 10-1, and I believe you can do the 10-2 homework. I think you can do all the homework. What do you think? Can you do all the 10-2 homework now?
This looks like what was on there.
Yeah, you could do the 10-2 homework, orientation, doing the parametric forms, those kinds of things, eliminating the parameter.
Maybe I'll even do 10-3. Yeah, me and Omar.
Good deal. All righty. Have a good weekend. See you Monday. We'll continue on Monday.